Alright, this is take like 15, and so I'm probably going to accidentally leave out some context. The reason is basically I've tried to read the editor's foreword to this book. This is a Calculus on Manifolds by Spivak, and I start rambling about the history of mathematics and the CIA and a certain somebody who didn't kill himself. It actually does tie into what was in the editor's preface, but I'm just botching too many takes, so we're going to skip the editor's preface and just go straight at the preface, which is before the table of contents. This little book is especially, so this is part of the GlowieMath playlist. GlowieMath is anything that includes CIA limits, CIA real numbers as sort of primary abstractions, and they're important, they're a weak point of mine, they're important in the modern formulation of physics, which of course I want to fix, and mostly following Norman Weilberger's program. Let me turn off this light, because that's annoying. This little book is especially concerned with those portions of advanced calculus in which the subtlety of the concepts and methods makes rigor difficult to attain at an elementary level. I'm going to actually turn this around. I'm going to turn it on. Let's try that. There, that's better. The approach taken here uses elementary versions of modern methods found in sophisticated mathematics. The formal prerequisites include only a term of linear algebra, a nodding acquaintance with the notation of set theory, and a respectable first-year calculus course, one which at least mentions the least upper bound supremum and greatest lower bound infimum of a set of real numbers. Beyond this, a certain latent, perhaps latent, rapport with abstract mathematics will be found almost essential. The first half of the book covers that simple part of advanced calculus which generalizes elementary calculus to higher dimensions. Chapter 1 contains preliminaries, and chapters 2 and 3 treat differentiation and integration. The remainder of the book is devoted to the study of curves, surfaces, and higher dimensional analogs. Here, the modern and classical treatments pursue quite different routes. There are, of course, many points of contact, and a significant encounter occurs in the last section. The very classical equation reproduced on the cover, let's look at the cover. This, I can't read that. Where's the cover? Appears also as the last theorem of the book. This theorem, Stokes Theorem, has had a curious history and has undergone a striking metamorphosis. The first statement of the theorem appears as a postscript to a letter dated July 2nd, 1850, from Sir William Thomson, Lord Kelvin, to Stokes. It appeared publicly as question 8 on the Smith's Prize examination for 1854. This competitive examination, which was taken annually by the best mathematics students at Cambridge University, was set from 1849 to 1882 by Professor Stokes. By the time of his death, the result was known universally as Stokes' theorem. At least 3 proofs were given by his contemporaries. Let me blow this up, sorry. Contemporaries. Thomson published one, another appeared in Thomson and Tate's Treatise on Natural Philosophy, and Maxwell provided another in Electricity and... Oh, I gotta read that. That would be fun to read. In Electricity and Magnetism 13. Since this time, the name of Stokes has been applied to much more general results, which have figured so prominently in the development of certain parts of mathematics that Stokes' theorem may be just considered a case study in the value of generalization. In this book, there are 3 forms of Stokes' theorem. The version known to Stokes appears in the last section, along with its inseparable companions, Green's theorem and the divergence theorem. These 3 theorems, the classical theorems of the subtitle, are derived quite easily from a modern Stokes theorem which appears earlier in Chapter 5. What the classical theorems state for curves and surfaces, this theorem states for the higher dimensional analogs, manifolds, which are studied thoroughly in the first part of Chapter 5. This study of manifolds, which could be justified solely on the basis of their importance in modern mathematics, actually involves no more effort than a careful study of curves and surfaces alone would require. The reader probably suspects that the modern Stokes' theorem is at least as difficult as the classical theorems derived from it. So I've been saying that, this is an aside, I did a video on abstract algebra in the abstract algebra series where I said quotienting was sort of the most fundamental idea in mathematics, and then there's this other related idea in quotienting, which is basically Stokes' theorem. And I'm having trouble articulating the point, but this is related to that quotienting thing. And then when I think I'm going to talk some about algebraic topology a bit, and that might help clear things up. Anyway, on the contrary, it is a very simple consequence of yet another version of Stokes' theorem. This very abstract version. Okay, let me reread the paragraph. The reader probably suspects that the modern Stokes theorem is at least as difficult as the classical theorems derived from it. On the contrary, it is a very simple consequence of yet another version of Stokes' theorem. This very abstract version is the final and main result of Chapter 4. It is entirely reasonable to suppose that the difficulties avoided so far... God, I can't read at this level, I'm sorry. It is entirely reasonable to suppose that the difficulty so far avoided must be hidden here, yet the proof of this theorem is, in the mathematician sense, an utter triviality, a straightforward computation. On the other hand, even the statement of its triviality cannot be understood without a horde of difficult definitions from Chapter 4. There are good reasons why the theorems should all be easy and the definitions hard. Well, that follows functional programming, is you have hard definitions, easy theorems. As the evolution of Stokes' theorem revealed, a single simple principle can masquerade as several different results. The proofs of many theorems involve merely stripping away the disguise. The definitions, on the other hand, serve a twofold purpose. They are rigorous replacements for vague notions and machinery for elegant proofs. The first two sections of Chapter 4 define precisely and prove the rules for manipulating what are classically described as expressions of the form, the differential forms. pdx plus qdy plus rdz, or pdxdy plus qdydz plus rdzdx. Chains defined in the third sections, and partitions of unity, already introduced in Chapter 3, free our proofs from the necessity of chopping manifolds up into small pieces. They reduce questions about manifolds, where everything seems hard, to questions about Euclidean space, where everything is easy. Concentrating the depth of a subject in the definitions is undeniably economical, but it is bound to produce some difficulties for the student. I hope the reader will be encouraged to learn Chapter 4 thoroughly by the assurance that the results will justify the effort. The classical theorems of the last section represent only a few, and by no means the most important, applications of Chapter 4. Many others appear as Many others appear as problems, and further developments will be found by exploring the bibliography. The problems and the bibliography both deserve a few words. Problems appear after every section and are numbered like the theorems within chapters. I have starred those problems whose results are used in the text, but this precaution should be unnecessary. The problems are the most important part of the book, and the reader should at least attempt them all. It was necessary to make the bibliography either very complete or unwieldy, since half the major branches of mathematics could legitimately be recommended as reasonable continuations of the material in the book. That's why I was saying this is sort of the most fundamental ideas, the Stokes' theorem. I've tried to make it incomplete, but tempting. Okay. Many criticisms and suggestions were offered during the writing of this book. I'm particularly grateful to Richard Palais, Hugo Rossi, I thought that was a fashion designer, Robert Seeley, and Charles Stannard for their helpful comments. I've used this printing as an opportunity to correct many misprints and minor errors pointed out to me by indulgent readers. In addition, the material following Theorem 3-11 has been completely revised and corrected. Other important changes, which could not be incorporated in the text without excessive alteration, are listed in the addenda at the end of the book. Michael Spivak, Waltham, Massachusetts, March 1968. Okay, right at the end of the era. Wow. So let's look at the table of contents. Let's zoom out a little bit. So we have the editor's foreword, which I couldn't get through without botching the take, because I started... Anyway. Functions on Euclidean space. Okay, this first one is like review material that is basic mathematical literacy. Differentiation, alright. Integration, alright. Integration on chains. Okay, so chapters 4 and 5 I think are the heart of the book, and I'm going to have some difficulty with this, but we'll see. And I might what I might do is rewrite this try to rewrite it without using the real number idea, but we'll see. I also got to buff up on Wildberger's recent stuff. He's been talking about Bezier. He calls them decastrated Bezier curves, and I can't pronounce that one guy. Declastajow, something like that. Bezier curves. And apparently those are like there's way more to those than I realized, and so I gotta go look into those. Anyway. I haven't been keeping up on my Wildberger. Functions on Euclidean space, norm and inner product. Okay. How long is this? Ooh. Okay, this is very dense. Okay, let's just kind of. We might skip this. We'll see. Let me just kind of look. Okay, we're not going to read through this whole chapter because there's so much there. Okay, Euclidean n space Rn is defined as the set of all n tuples of real numbers xi, and a one tuple of numbers is just a number, and R1 is the set of all real numbers. An element of Rn is called a point in Rn, and R1, R2, R3 are often called the line, the plane, and space, respectively. If x denotes an element of Rn, then x is an n tuple of numbers, the ith one of which is denoted x to the I, thus we can write x is equal to x1 up to xn. A point in Rn is also frequently called a vector in Rn because Rn with x plus y defined in the usual way, and scalar multiplication defined in the usual way as operations, is a vector space over real numbers of dimension n. Go watch my abstract algebra playlist. In this vector space there is the notion of the length of a vector x, usually called the norm. Bar x of x, and defined by abs x, is the Euclidean norm. Oh, you know, the other thing we're going to read is the data mining book. If n is equal to 1, then abs x is the usual absolute value of x. The relation between the norm and the vector space structure of Rn is very important. Okay. Theorem 1.1. If x and y are in Rn and a is in R, then the absolute value of x is greater than or equal to 0, and abs x is equal to 0 if and only if x is equal to 0. Okay, yeah, because it's a sum of squares, so you're going to get a square root of something that's a sum of things that are either greater than or equal to 0. Okay, yeah, that makes sense. And the only way that that is 0 is if everything is 0. Okay, yeah. This is like the Cauchy-Schwarz inequality, I think. Yeah, the absolute value of a dot product is less than or equal to the product of the lengths. Right, because one way to see this is the dot product is defined as the product of the lengths if you go by CIA physics. So let me draw this out. So this quantity here, this quantity in here is called the dot product of, let's call it x, the vector x dot y Okay, let me make the pointer smaller. X dot y is the dot product. This can be defined as in CIA world as the the way the physicist would write it is xy, so where if you don't put the vector hat you mean the length, xy times the cosine of the angle between them. Or in other words, let's use x dot y. This is the naked things with no hat, no arrow mean the length, so times something that is between -1 and 1. Okay. Okay, and if we take absolute values of both sides, okay, then the absolute value of a product is the product of the absolute values, so this is equal to abs x, abs y, times the absolute value of a cosine theta. Okay, but this is obviously, because the cosine, absolute value of cosine will range between 0 and 1, this is less than or equal to abs x, abs y. Okay, and thus we've proven the theorem. Okay, yeah. If you go by the CIA physics definition, but that's a good enough definition, because physics works a little bit better than math, I would say. This, I think, is the Cauchy-Schwarz, and one of these is Cauchy-Schwarz. Yeah, this is what I was saying. Well, I wrote it differently, but yeah, so this is wonderful. There's no notational distinction between vectors and numbers, except you maybe use these letters for numbers and these letters for vectors. But anyway, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Okay. So, 3, I'm trying to think of a proof with square roots, because it'd be x squared, so you can write, so this is for part 2. And for part 3, I think part 4 is pretty obvious. For part 3, let's do x plus y. These are vectors. So, okay, I hate this absolute notation. Okay, let's think about it this way. That if we square both sides, we would get, if we square both sides of this, since these are both positive quantities, we would get the quadrants is a lot easier to work with. The quadrants of x plus y is less than or equal to, if we can prove this statement, then the other statement is true. Quadrants of x plus the quadrants of y plus 2 times the absolute value of x, because the quadrants is the length squared, times the length of y. Okay, and this is just the binomial theorem, because I just squared both sides of that. So these two statements are equivalent. This statement and this statement. Okay, the quadrants of x plus y so this would be the sum of xi, I'm going to use subscript notation, plus yi squared, and we're trying to prove that this is less than or equal to the sum of xi squared plus the sum yi squared plus 2 times the square root, or not the square, sum I squared 1/2 sum yi squared 1/2. Okay. Okay. And if we break up the sum on the right, we would get the sum of xi squared yi squared plus 2 times the inner product of x and y. Ah! I'm just rewriting the right-hand side of the equation. Plus 2 okay, well, if we cross out this and this because they're the same, this and this because they're the same, and then we cancel out the 2's, we just get part 2. So part 3 reduces to part 2. Okay. And then part 4 I think is fairly obvious if you just plug it in. Okay. I didn't think about equality holds if and only if x and y are linearly independent. So if we go back to the physics idea, then equality would hold if and only if the cosine was equal to plus or minus 1. Cosine is plus or minus 1 when the angle is either 0 or 180 degrees. So, yeah, okay. So that makes sense. But, let's see. 2, if x and y are linearly dependent, equality clearly holds. Because then, like, right, because then y is equal to a multiple of x, and then you get a sum x of x squareds. I gotta think about that. Anyway, I don't know. I'll just go with my physics explanation. If not, then lambda y minus x is not equal to 0 for all lambda, okay? Right, that's the definition of independent. 0, right, because this is not equal to 0 and it's strictly positive. Is equal to, right, he's switching to a quadrants here. Okay. Ah, now he's using polynomial stuff that I don't remember. Okay, but let's... Okay, therefore the right side is a quadratic equation in lambda with no real solution. Ah, right, because this is always positive for every lambda. For every lambda, this is strictly positive. So that quadratic equation has no real solution. And so its discriminant must be negative. Okay, I don't remember the logic with discriminants, but let's just accept that. Thus, the discriminant there is negative. Ah, okay, and then you just move that over and you get the theorem. Okay. Okay. I think this is the same logic that I just did right here. Okay. Yeah, this works. The inner product, I called it a dot product, same thing. The inner product, let's see, what are the properties? It's symmetrical, it's bilinear, it's not just linear, it's bilinear. It is positive definite, okay. Yeah, right. This is the Hilbert polarization identity. Okay. Okay. I don't feel like going through the proof of the polarization identity is the only one that isn't obvious. Oh, 3 and 4 are left to the reader. Lovely. Oh, there's polarization. Hilbert, that's damn it, I think it's the Euler 4 square identity. Let me look that up. I think it's the same identity. Nope. Is it the 2 square identity, maybe? I don't know. 4 square identity, I remember that's interesting. Okay. But yeah, you take the quadrants as quadrants of x plus y, you can write that out algebraically. Quadrants of x minus y, you write that out algebraically. Probably everything, the x squareds will cancel, the y squareds will cancel, I bet. And then you get 4xy, you get a sum of 4 times the dot product, and that's why you divide by 4. Okay. Probably that's what happens. Okay. Anyway, makes sense. We conclude this section with some important remarks about notation. The vector 0 will be denoted, okay, simply 0. The usual basis of Rn is that, right? If T is a linear transformation, the matrix of T is the m by n. Okay, so you're multiplying by a column vector, okay? So m rows and n columns, which means that you multiply by an n length column vector if you think of it as a single transformation. Where T of EI, the m by n, where T of EI is why does it swap the J and the I? I don't feel like okay, we know how to multiply matrices, okay. Okay, we all know what matrices are. Okay, I'm not gonna Okay. I'm going to do some of these problems on my own. Go by the book. I will see you in the next video. Thank you for watching. This has been... Alright. See, these books are tough. They're dense. But I like that. Anyway, this is a classic book. So, and I want to read through all of Spivak, actually. Anyway, that's all I have to say. Thank you for listening. Good night.